Hi CTM students, welcome to the practice test for Chapter 1. You're going to see me go through the entire Chapter 1 practice test here, question for question, thought for thought. And you can kind of pause and rewind as you need to reflect, review upon the ones that you may be struggling with. You don't have to watch it all, but if you want some more practice after this, after we go through the practice test here, feel encouraged, highly encouraged, to check out these problems in the Chapter 1 review on these pages 35 to 38 in your textbooks right before the practice test. All those answers are in the back as well. So here's the practice test that we're going through. Got 2 pages to 18 questions. I'm going to be doing most of these questions, or all of these questions, for the first time. I'm just looking at them right now. And so you may see me kind of hash my way through things, maybe even struggle a little bit through things, and that's just how these problems are. Sometimes you have to think about different ways to do them, to brainstorm different ideas, problem solving, the chapter that we're working on right now, working through. That's just how math is sometimes. You gotta think it through. Okay, so let's check out exercises 1 and 2 here, using inductive reasoning. So just looking at the patterns, in other words, to determine the next 3 numbers in the pattern. So 3 numbers in this pattern. It looks like just here plus 3, plus 3, plus 3. So what's 15 plus 3? 18. And then keep going, 21 and 24. That's all we got to do right here. I'll just write off to the side here what the pattern was. The pattern was plus 3. And then number 2, what's the pattern there? It's a little small there, but hopefully you can read that. You can check out your book too. It says 1 1/3, 1/9, 1/27. So it looks like the denominator is getting multiplied by 3 here. Next up, I would have 1 over 81. Then I would have 1 over 2, 43. And then I felt like maybe I had that one memorized, but no, there it is. Okay, so 1 over 729. I do remember that now that I typed that into the calculator, that would be that times 3. Okay, so here the pattern was times 3 with the denominator. So with inductive reasoning, with a problem like this, it's a mega M, the denominator. There we go. With pattern problems like this with inductive reasoning, check for the pattern, see what the pattern is, and just continue that pattern to the next ones. Alright, let's check out number 3 now. It says, pick any number, multiply the number by 5, and add 10 to the number. Divide the sum by 5, subtract 1 from the quotient. Alright, breaking it into 4 different parts here. And I'll just go with black instead of the red I started with. I might use red to make little notations with stuff as I continue from here. What is the relationship between the number you started with and the final answer? So let's pick any number. Let's do what it says. Pick any number, multiply the number by 5. So let's go with a pretty easy one to deal with. I'm going to go with 2. That seems pretty easy to deal with. So I'm going to say 2. 2 times 5 would equal 10. And then, so you don't think that I'm just saying 10 plus or times or whatever equals this. I'm going to put a little semicolon there. Multiply the number by 5. Did that. Add 10 to the number now. So take 10, new number plus 10 would be 20. And then with that number, divide the sum by 5. So that's the sum. Taking that, divide it by 5, I get 4. And then finally subtract 1 from the quotient. So 4 minus 1, the quotient was the answer part there with the division part. So it looks like 3 is my answer. So what's the relationship between the number you started with and the final answer? My guess, I'm going to make a conjecture. Actually, that's in the 3rd part here. So what's the relationship? It's the number I started with plus 1. I don't know if that's going to continue. It looks like it's the number I started with plus 1. I'll put the original number plus 1. That's at least what I noticed about 2, so I started with 2. Here, and so then I got the original number plus 1. Alright, arbitrarily select some different numbers, repeat the process. It doesn't say how many times we have to repeat the process, so I don't want to do this 2 more times. So I'll start with, I'll go with a little bigger number. Let's say 7. 7 times 5 would be 35. And then That's plus 10 would be 45. 45 divided by 5 would be 9. And 9 minus 1 would equal 8. So the pattern seemed to hold. It was original number plus 1 again. That was my final answer. I should get in good habits here. I want to box that in. Alright, so that held for that one. Let's pick a larger number, a little more obscure one, maybe 19. How does that sound? So 19 times 5, 20 times 5 would be 100. 19 times 5 would be 95 then. 95 plus 10, that's 105. 105 divided by 5, that's going to be 21. 21 minus 1 is 20. So seems to hold again. So it just says record the original number and the results. So I started here, I ended here. I started here, I ended here. So it seems to hold. That's my conjecture. The conjecture is that it's the original number plus 1. So I'll write it like this. It's always the original number plus 1. That's my conjecture. And in part D, we are supposed to prove using deductive reasoning the conjecture made in part C. So how can I prove this? In other words, I have to prove it's always going to be true. How can I do that? I can start with a variable. I'm going to call my variable, I'll go with x. And so x, and then just so you don't think it's x and then another x, I'm going to put the dot for multiplication to start here. So x times 5 will be 5x. 5x plus 10 would equal just that, 5x plus 10. And then if you took 5x plus 10 and divided it by 5, so 5x plus 10, I could write that like this. I could say divided by 5. That's another equivalent way to write divided by with a fraction bar. This and this would cancel. I'd be left with x. And then this would be a 2, x plus 2. And then finally, I'm going to bring this thought over here, x plus 2. If I took that minus 1, I would end up with an answer of x plus 1. And so did that prove my result? Yes, it did, because I started with x and it ended up with x plus 1. Whatever number I start with doesn't matter. I'm going to have that number in the end plus just 1. So that proves the result there, going through steps like that. I could have written these things vertically, but I just wrote them horizontally like this. Hopefully you could do it either way, so it wouldn't make a difference there. Number 4 and number 5, we're supposed to estimate. So we do not have to figure these out exactly. Shouldn't see calculators on this. I'm going to leave the calculator alone, and I'm just going to say that this is approximately what I see here. That looks like it's about the same as, I could round this off, but I noticed that this one I could definitely round off. I'm going to keep this like that. I'm going to take this and make it 100,000. So we're going to get some slightly different answers here. You may have gotten something slightly different than what I got here. But I know that if I multiply 6 times 100,000, I would get 600,000. And then I would just have to move the decimal 2 spots. And so 600,000 would become 6,000 if I'm going to multiply it together and move the decimal 2 spots. And so if you check the back of the book, I just checked that right there as I looked at that, and that's what they had to. So they didn't round off the 6, but they did round off the 98,000 to 100,000, it looks like. And so if that was unclear to you, remember that this is the same thing as, you can think of it as, this is kind of how I thought about it. It was 600,000 if I multiply by 6, but then you got to move that decimal 2 spots because it's 0.06. So think of it like that, if that helps you. And then 102,000 divided by 0.00302. So what would that be? 102,000 divided by that. I know that's 102,000. That's pretty close to 100,000. But I also know that, I'm going to leave it like this for right now. That number in the bottom, I definitely want to get rid of this 02 at the end and think about it more like this. Okay, and so from there, what can we do there? I can think of this as, let me do this in a different color here just so it stands out a little bit more. I know that if I divide by a decimal, I can make this a little easier to think about by moving that 3 decimal places. So that's going to change that to that. I'm going to have 3 more decimals there. So this would be the same as 102 million divided by 3. 102 million divided by 3. I know that 102 divided by 3, I know 99 divided by 3 is 33. So I know 102 divided by 3 would be 34. And so my estimate, just mental math with estimation, we should be just using mental math as much as possible. My estimate would be about 34 million. I look in the book and they say 33 million. I think this is how they arrived at that. They probably rounded this off to either 100 million or 99 million, something like that. You could think of it like this. Now if you said 100 million divided by 3, that would be 33.3. That's about the same as 99 million. So this is what the book looks like they're considering, or this is looks like how they're considering to. I can't talk right now. It looks like this is how they're coming to the answer. How's that? I'll just leave it like that. So they had 33 million in the back instead, because 99 divided by 3, 33. And so you could say that as well. As long as you're pretty close with your estimate. Estimates are just in the ballpark, as long as you're pretty close with those and you did legitimate work here, you didn't estimate in a way or round off in a way that's not allowed, then you're good to go with that. Alright, let's check out number 6, estimating area. Hopefully I'll be able to speak more clearly on this one, not garble my words there. If each square represents 1 square unit, estimate the area of the shaded figure. So I look here and I see this square, and this square, more or less. There was a tiny little sliver gone, but those are basically 3 full squares. Now if I put this together, so that's what I would say it would be like 1, 1, and 1. These ones look to be about a half. So that's like a half and a half. And then to me, it looks like if I put these 3 together, 1, 2, 3, this might come up to be 1 whole, those 3 together, because there's a sliver missing here, but there's a tiny little sliver here and here that I could kind of cut this triangle out and fill in that gap there. So that's what I'm seeing there. I'd say this is about a half and a half together. So these 2 coming together making a whole, these 2 coming together to make a whole. And I would, let's see, this is just an estimate again too. So estimating, we're just estimating the area here. I would say that I could probably put, this one is almost a whole, so I could probably put this one together with this one, and that would give me a whole. So far I've got 1, 2, 3 in the middle here, 4, 5, 6, 7, and then maybe put these together. Somewhere between 6 and 7 I think would probably be the best answer. So if I rounded up, I'd go to 7. So I think the best answer here, you could say, number 6, somewhere between 6 and 7. I just looked at the book. It doesn't give me units, so I would just say units. I could leave those out, so I'll kind of put that in parentheses to signify that if it's not included, you wouldn't have to include the units. This would be units squared, though it's an area. So units squared, 6 and 7 units squared. The book has 7 units squared, and you can kind of see how they may have arrived at that. So I should have said between 7 and 8 actually. This would be 1, 2, 3, 4, 5, 6, 7, and then I feel like there's a little left over here. So I would say between 7 and 8 actually. Let me I want that squared back there. But we'll erase that, and I think that's probably the best answer. The book says 7. I think that's a pretty good estimate as well. Alright, let's check out number 7 here. Body Mass Index, BMI. During the week of June 12, 2001, the federal government updated its method for determining if a child is overweight. To make this decision, first determine the child's body mass index, or BMI, then compare the BMI with one of the 2 charts, one for males and one for females, provided by the government. On the right, we give the chart for males up to age 20 to determine a child's BMI, and then you go through these steps. Divide the child's weight in pounds by the child's height in inches, divide the results from part 1 by the child's height again, and multiply the results from part 2 by 703. Okay, so Richard is a 14-year-old male who weighs 130 pounds and is 63 inches tall. So determine his BMI. And so it looks like they want us to use these 3 steps. This is what it seems to me after reading that whole question. I should go through these whole steps. It doesn't look like it's going to be here as well. That's what I'm going to look at later in the graph. So I'm going to go through these 3 steps for number 7 here. So a 14-year-old male weighs 130 pounds, 63 inches tall. So divide the child's weight in pounds by the child's height in inches. So his weight in pounds is 130, height in inches is 63. And that, I'm going to use a calculator for that part. 130 divided by 63. I want a pretty exact number here. So I'll round this off. Why don't I go 4 or 5 decimal places? I'm going to keep this pretty long for right now. I want a more exact or more precise answer for as long as I can keep that precise. So 2.06349. Why don't I write that? 2.06349. This decimal continues. I'll put a little dot there for that. So this is step 1. Step 2 is to divide the results by the child's height again. So we're going to take this value. Why don't I actually just keep this in my calculator? So I'm going to keep this value in my calculator, and I'm going to divide that again by the child's height. So I'll take this divided by 63 again, and I get this value. Okay, so 2.06349, and the dot I think is good to represent that. That continues. I just kept that in my calculator and divided it again, and so this is going to be 0.03275, blah blah blah. It keeps going. Okay, so 0.03275, and it keeps going. I'm going to keep it in my calculator one more time, and then step 3, multiply the result from part 2 by 703. So this times 703, that equals 23.02. So I'm going to round this one off to the nearest hundredth. I'll go 23.0. Since that's a 5, that's 5 or higher, this would get rounded to a 3. So this is approximately 23.03 for his BMI, body mass index. Alright. And then that's parts A right here. So this is part A, the 3 steps. Part B, does he appear to be at risk for being overweight, or is he overweight? Explain. So overweight would be this orange, and then the green would be at risk. Here's 14, and if we go up there, and we're matching up his BMI, so 23, just a little above 23, that looks like right about there. And so according to this, that means Richard is, in this green section, at risk for being overweight. So that's what we would say here. He appears to be at risk. Now, just a little side note about BMI. I don't like it. I think it's a poor measurement because it does not take into account musculature. If somebody is just has more muscle mass than somebody else, I know myself, my BMI, it says that I am at risk for being overweight, and I feel like I'm anything but being at risk for being overweight, just because I have kind of more muscle mass, especially in my legs. I have strong legs, and I get knocked down, or the government says I'm almost overweight because of that. So I don't like BMI, but the math behind it, this is how it works. So anyways, enough of my ranting about BMI. Let's look at number 8, gas usage. Gas company charges $9.63 for the basic monthly fee, which includes the first 3 therms of gas used. It charges 72 cents for each additional therm used if the Smith's gas bill for the December was $122.13. How many therms of gas they used during the month. So to me, looking at this problem, just thinking about that a little bit, I think the best way to do this would be in kind of an algebraic way. Let's say x equals the amount of therms and we'll say past 3 therms, excuse me, for lack of a better way to state that. That's just what's coming into my head right now. Because that first 3, it's part of their 963 monthly fee that they have to pay no matter what. Even if they use no gas at all, they still have to pay $9.63 just for having the possibility of using the gas. So let's take this. We would say in an equation we could say $9.63. So that basic monthly fee plus, and it's 72 cents for each additional therm used past the 3 therms. So this would be 72 cents times X. So X is something past the 3 therms. We're multiplying that times 0.72, 72 cents. This apparently equals 122.13. And so this is the basic monthly fee. This is the therms after 3, and we get this. And so this becomes an algebra problem at this point. We can subtract $9.63 from both sides. That leaves us with the 0.72x is going to equal, and that's not one I'll do in my head. I'll work this one out in the calculator. 122.13 minus 9.63. That was not right. I missed my decimal in there. Let me just use a keypad instead. Sometimes the pen doesn't work so well when I'm typing into the calculator for whatever reason. Minus 963, there we go, 112.50. So $112.50 in other words, and we're taking that value, dividing it by 0.72, and that leaves us with, take this, divide it by 0.72, and we got 156.25. .72, what the heck am I doing? 0.2572 is right here. I looked at that. Okay, so this is the amount of therms. X is the amount of therms after the first 3, remember. So after the first 3 therms, I'll say. And so what's the total amount of therms? How many therms of gas? So we would say total therms would have to be that number plus 3. And so you would say 159.25. Don't forget your units when you have problems like this. When we have real life applicable problems, we want to include those units so that people know what we're talking about. So 159.25 therms. Number 9, cans of soda. At a local store, a 6-pack of soda costs $2.59, and individual cans cost 80 cents. What is the maximum number of cans of soda that can be purchased for $15? So if you took 80, this is just a side thought over here, and you multiplied it by 6, let's just make sure that the individual cans aren't cheaper. And so this would be 480. We would have that. 2 total decimal places up here, so 2 total decimal places there. You're going to have a 0 for that last one. So this is 480. So do we want to use individual cans? No, we can get them way cheaper in a 6-pack. If we're going to buy 6 of them, we should get the 6-pack. So that just means, I'm going to cross it out. That means don't use that idea. We don't want to just get individual cans. And so from here, I would say, well, how many 6-packs can I get? I want to decide that first. So let's take 15 and divide it by 259. So 15 divided by 259 is going to equal, let's put that into a calculator. Basically, I'm going to figure out what my remainder is. What is my remainder? And go from there. So 15 divided by 259, that's going to give me 5 and some change. So I can't split up that 6-pack, so I'm going to have 5 6-packs with some left over. So we have a remainder. So this is $15 divided by 259. So if you take 259, multiply it by the 5 6-packs, whole 6-packs you can get. Let's do that and see what that is. So this, there we go, 259 times 5, that'd be $12.95. So $12.95 for the 6-packs. And just kind of doing this as it's coming to me. There might be different ways to go about this, or different ways to organize your thoughts. But this is that much for the 6-packs, which would mean you would have $2.05 left over. Okay. And so the remainder is $2.05 here. And so how much can you get? How many cans can you get with that much? So 205. If you divided that by the 80 cents, you could get 2 more cans. 2 individual cans. And the 2 individual cans, just as a side note kind of here again, 80 cents times 2, that'd be $1.60 for the individual cans. And you'd have 45 cents left over. And so you've got, what is your total number of cans you can purchase? You got 2 here, and then you have 5 6-packs. So your final answer should be the 5 times 6, that for the 6-packs, plus 2, you would have 30 plus 2, which would be 32 cans. So if you check that out in the back, you see that's the correct answer, and we can move on from there. Right, number 10, cutting wood now. We have, how much time does it take Carla Nab, a carpenter, to cut a 10-foot length of wood into 4 equal pieces if each cut takes 2.5 minutes? I'm going to do something wrong here. See if you can figure out what I'm doing wrong. This is what I think most students that would get this one wrong would do. I think they would do this and be like, oh, okay, 4 times 2.5, that's 10 minutes. And why is this wrong? Why is this the wrong answer? Because you're not thinking about the problem really first. You're not thinking about this in context of a picture or in context of what we're really talking about. So why don't I draw a piece of wood here? This is going to be the fill color. Yep, I'll leave it like that. And so this will kind of represent that. So you've got this 10-foot long board. So from here, from edge to edge, from here to here, it's 10 feet. We're cutting this into 4 pieces. How many cuts do we actually have to make? We need to cut it. You cut it in half, that would give you the 5 and the 5. If you cut it into 4 equal pieces, we cut it in half 2 more times. How many cuts are you actually going to make? 1, 2, 3. We only need to make 3 cuts. And so we have 3 cuts to make. Meaning that your final answer should be 3 times 2.5, or in other words, 2 times 3 would be 6, and then 1/2 times 3 would be 1.5. Put that together and you have 7.5 minutes. A little tricky problem there. At least you might think of that as a trick question, but draw a picture and think about it in the context of the picture, in the context of the real life situation. It becomes a lot easier to think about. Don't be fooled by something like that. Okay, number 10. We got this Van Gogh painting. This photo of sunflowers in 1889. 1 inch equals 15.8 inches on the actual painting. Find the dimensions of the actual painting. Alright, so I had to pause the video for a moment there because I realized I didn't have a ruler, and I needed a ruler for this one. I just measured this in the book. I didn't measure it here because I've adjusted the size of the pictures here. This is 2.5 inches in the book. And then this distance from here to here is 1 7/8 of an inch. So 1 7/8 inches in the book. And 1 inch equals 15.8 inches on the actual drawing. Find the dimensions of the actual painting. So I would take this number for the width. I would want to take that number, 1 7/8 times 15.8. And so what would this equal? I could change this into a fraction, an improper fraction. That's what I'm trying to say there. So 8 eighths plus 7 eighths would be 15 eighths. 1 is the same as 8 over 8. So I'd have 15 eighths times 15.8. That's a little easier to type in to a calculator at this point. And so I'd take 15 divided by 8. That's the same as 15 eighths. And I take that number times 15.8. That leaves me with about 29.625. So 29.6 if I'm going to round that off. It doesn't say how I have to round it, but 29.6.625 is actually 29 and 5/8 if you wanted to get real technical, but it's approximately 29.6 inches for the width. And then the length, or going this way at least, the height of the picture, maybe you could say, height is going to be probably better to say height than length. I would say width and height of the picture. This would be 2.5 times 15.8 again. You could make this 5 halves. You could write it like that. You could write it as a decimal as well. That one's a little easier to think of in your head as a decimal, I hope. 1/2 is the same as 0.5, so you have this times this, which is approximately 2.5 times 15.8 is going to be 39.5. So 39.5 inches. And I could get rid of that squiggly equal sign there. That one exactly was 39.5 inches. And so you have 29.6 by 39.5 inches. Okay, number 12. Moving on. Payment shortfall. Monica Wilson gets $12.75 per hour with time and a half for any time over 40 hours per week. She works a 50-hour week and gets paid $652.25. By how much was she underpaid? Ooh, she got underpaid. Man, that's not good for Monica. All right, let's see, Monica, what happened? How much did you get underpaid by? So number 12, here we've got $12.75 per hour. So I'm just going to write down the thoughts, brainstorm the thoughts as they come. And then for overtime, we're supposed to be making a time and a half. So we're supposed to take 12.75 times 1.5. That's a time and a half. That would equal 12.75 times 1.5. Should be 19.125. So 19.125. This would be dollars per hour here. So that much per hour normally, you could say, and then overtime is that much. And so we might be rounding this off to $19.13. I imagine that's what we'll do here in a second. So let's call that 19.13. Let's do that here. I'm guessing that's probably what the book would have us do. So if she works a 50-hour week, gets paid $652.25. How much was she underpaid by? So this was the total paid that she got, and we want to kind of keep that separate from the thoughts over here. So 40 hours is a normal week, so 12.75 times 40 would be normal, plus the overtime she worked, plus the 19 point. Why don't I keep it exact? Maybe they will keep it exact. I'm curious as to how precise they wanted us to be with this. So I'm going to leave it like this. This is the normal hours. I'll do this in a different color. So this was the normal, and then this was the overtime. And if it doesn't jive with what the book has here, we'll try the 1913 instead of the 19.125. So this times 40, let's see what that is. 12.75 times 40 is going to give me 12.75 times 40, 510 for the normal work week. And then times 10 here, I just move the decimal one spot. So this would be plus 191.25. And so if we add that together, we would have, this would be 500 plus that would be 691, so this would be 701.25. And it looks like this probably was the better way to go about it. Yep, so that's looking at what the book has. So this is what she should have been paid. This was the amount she should have been paid. And so to figure this problem out in the end, we would take this minus the amount she actually got paid, and we would see that that's $49 exactly. So $49 not unpaid, but underpaid. There we go, underpaid. Monica, you need to teach your boss how to do some math, alright? Bad boss, bad. Don't underpay your workers. If you become the boss someday somewhere, make sure you give your workers the wages they deserve. Number 13, magic square. Create a magic square by using the numbers 5, 10, 15, 20, 25, 30, 35, 40, and 45. The sum of the numbers in every row and column and diagonal must be 75. And so our little trick with magic squares, something we learned earlier, the middle value should be the sum divided by, there's what you should be getting with the sum should be the sum divided by 3. So in this case, 75 divided by 3, that middle number I should put 25 in the middle. So 25 goes in the middle here. Alright, let's make a little square here. Like this. Whoa, I didn't want to fill that. I want that unfilled. Okay. And make some horizontal and vertical lines for that. Alright, that's good enough, and let's fill in the values here. So 25 I'm feeling like is where that's going to go. These could vary quite a bit in terms of the values that go around here. Just got to start somewhere though. So I want to start with 25 in the middle, and why don't I go with, I'll just try a value here. I'll go with 10. And this might not work the first time. That's part of math. Part of math sometimes is trying something, seeing that it doesn't work, trying something else. Keep trying it until you get something that does work. So 25, and this, I would have to get 40 to get the sum. They tell me that the sum is 75 for each row. Every row, column, and diagonal must be 75. So this plus this is 35. Left over would be 40. All right. So let's try something else. I'm probably going to have to change some of this stuff around a little bit, but why don't I try, I'll go with 5 here. Alright, so 40 plus 5 would be 45. What would be left would be 30 right here. And so let's see if I can get something that works here. This would be 40, and then I would have to add 35 more to get that. 35 plus 25 would be 60, so that would be 15. Maybe I'm going to get lucky here. This would be 55, and this would be 20 then. And so what do I have left over? I still have a 45 left over in my choices. Let's see if it works. This would be 30. This would be 75. Added together, does it work this way as well? Let's see. So this would be 60 or 70, sorry, and 75. That works that way. Does it work this way? We got 50 and 75. Yep, and it works this way. And so I'm going to check, just double check all of them again. This is 75 this way. That's 75. That's 75. This is 75, this is 75, this is 75, and it's 75 along the diagonals as well. So hey, I got it to work. I got it on the first try. Feeling pretty good about that. But if it didn't work on the first try, you're going to have to erase some things, try some things in a different arrangement, try some things in a different way. But starting off with this number in the middle, 25, that's the key part. You want your middle value to be whatever the sum that's supposed to be. So the sum here was supposed to be 75. We want to divide that by 3. Okay, let's check out number 14 now. A drive to the beach. Mary Chin drove from her home to the beach, that is 30 miles from her house. First 15 miles she drove at 60 miles per hour. The next 15 miles she drove at 30 miles per hour. Would the trip take more or less or the same time if she traveled the entire 30 miles at a steady 45 miles an hour? There's an interesting question. I think I should still have it posted up at this point on Wagner Academy. I've got me hiking, and I ask a very similar question. If it's going to be faster for me to hike going slower uphill and then faster downhill, or just keep a steady pace. And so very, very related to this question. So let's say that we have our road here. I'll draw a little road. And let's use some of these tools here. So this will be my road to the beach. And The road, we'll say it's the blacktop. I don't want to fill that with black here. Okay, so here's the road to the beach. And here's my beach. Over here, we'll make this color in the beach over here. That is not a good looking beach. Alright, so we made it to here's the beach. Oh, that's beautiful. Okay, and then here's the ocean. The waves are rolling in. And oh, look at that. It looks beautiful out here. Okay, and this was Mary Chin's house over here. She's got a greenhouse. And she started driving on her vehicle. Alright. And so the first 15 miles, the next 15 miles, we're going to split this up into 2 equal parts. We're going to say that this is 15 miles from here to here, and then another 15 miles from here to the beach. Van Gogh right there. Yeah, Van Gogh artwork, no match for this. Let's see, so 15 miles, 15 miles. So at first she's driving 30 miles an hour from this stretch, or 60 miles an hour, sorry, from her house to the halfway point. And then we're saying 30 miles an hour from there to there. So I'm going to think about this in 2 separate parts for this first part. So think about, for this distance, speed equals distance over time. S equals d over t. So the speed is at 60 miles an hour, and the distance she's traveling is 15, and the time is t. So I'm going to write it like that. You can also think as time equaling the, I'm going to cross multiply this. So I'm going to have 60 times t equals 15. The time is the speed divided by, or the distance divided by the speed. Okay, so we have this divided by 60. Yeah. So time equals distance divided by speed, if you can think of it that way too. This would be 1/4 of an hour, or 15 minutes. Okay, and so here, how long is this going to take, this portion of the drive? Speed is still distance over time. You can think of time equals distance divided by speed, so why don't I write it like that this time around? If I wrote this as fraction cross multiplied, you think of it that way too. You could also hopefully intuitively think that, okay, I go X number of miles, divide that by the miles per hour, that's going to give me the time it takes to get there as well. So this is another way to think of it. You've got the distance 15 divided by the speed would be 30, and so this one you'd have half an hour or 30 minutes. And so total time here, we take these two values and we add them together, and we have 45 minutes total. Now if she was traveling at a steady rate of 45 miles per hour, let's make a comparison here. So we have time, it's the same thing as distance over speed. Speed is distance over time. Could you still use speed equals distance over time? If you can't remember this equation, go back to that, yeah, and plug it in. Do your cross multiplication if necessary. But time here, distance is, the whole distance is 30 miles. So the whole distance, 30 miles, over the entire speed for that would be at the 45 miles per hour. Would be like that. And so you'd have time here would be 2/3 of an hour. 2/3 of an hour is the same thing as 40 minutes. And so which way is faster? This way is faster right here. This is faster. And so our final answer, we would say, would it be more or less or same time? It would be less time. Right here, you can see that this is 5 minutes slower. So by 5 minutes. And intuitively you might say, well, that doesn't seem to make sense. I thought it would be the same because this is like the average of that. But remember, or think about this, you're going at this slower pace for a longer time. That means it's going to really stretch this time out from here to here. If you really made it ridiculous and said like 90 miles an hour, and well, I wouldn't want to go quite that high, but something really fast, you're going to cover this first 15 miles very quickly. But then if you went really slow, like 1 mile an hour, it's going to take you 15 hours to cover 15 miles if you're going 1 mile an hour. So think about that. That hopefully breaks your intuition, or what you might intuitively think, and helps you realize that it's actually going to take less time if you keep that steady pace. 15. Pick 5 numbers from the 6 numbers 2, 6, 8, 9, 11, and 13. Pick 5 that when multiplied give 11,232. And so this was the way I was just thinking as I'm reading that question here, that I'm going to try this first. This might not work out for me, but I think it's going to work out. So I know that this is an even number, so I'm going to say 2 times, what's 2 into 11,232? That's not what I want there. I got an extra 1 there. 11,323. 232 divided by 2, 5616. Okay. And so let's see if one of these other numbers go into there. Why don't I try and figure out which one doesn't go into there? That might be the easiest way to do this. So does 11 go into there? No, it doesn't. So I'm thinking that 11 is the one that's not going to work. Let's see if these other numbers go into there. So let's clear this out. 5616 divided by 13 is 432. So 13 here, 432 here. Let's split that up into, so 11 I knew didn't go into the bigger number, so it's not going to go into this smaller number. What's 432 divided by 9? That's 48. And I know that 48 is 6 times 8. So I see that's this times this times this times this times this. This isn't a completely factored factor tree, because I could break this into 3 and 3, so it's not the prime factorization, but this all multiplied together would give me what I started with. And so 11, no, sorry, what are the numbers? It would be 2, 6, 8, 9, and 13. Maybe some other day 11 you'll be included in a problem, but it's not this one. Alright, number 16, moving on here. One guess is off by 9 in this jelly bean guess. So one guess off by 9. Another guess is off by 17, and yet another is off by 31. How many jelly beans are in the jar? And so my guess is 260, 74, 34. I think we can use these as actual guesses. And so one of these is off by a certain amount, another one by a certain amount, another one by that third amount. And so just thinking through that for a moment, I'm going to see if this works. It might not work, but I think it's going to. So 260, I noticed 260, 274, and 234, these are the highest numbers. So I'm thinking that middle number is the one that's off by 17. I might not be quite right by that, or off by 9, I mean. Is that where I wanted to go with that? Yeah, so 260 minus 9, let's see if that works. So I used 9 up, so I have 9, 17, 31. I used 9 with that one. Let's see if I can get a value that's the same value with a plus 17 and a minus 31 from that. So 251, and so that's that value, off by 31. 274 minus 31. It looks like didn't get it to work out. So this one isn't the right combination. So I would say no, it's not that one. So I need to rethink this again. So I'm going to rewrite my values here and see if I can come up with the right combination with my next shot. Okay, so I think I got one that might work here. I'll try this one. Try 260 minus 17. So that one, let's see what that gives me. It gives me 243. And so 243, I know 274 minus 31, I already did that, was 243. So looking promising. If that last one, if 234 can be 9 away from that, and yep, if I add 9 to it, that would be it. And so what's the right combination, or what's the answer? The answer is going to be, or how many beans are in the jar. The answer, 243 would have to be it. Okay, so sometimes that happens. Sometimes you try something and it doesn't work out the first time. That just happened to be there. Even as a teacher, that's going to happen sometimes with problems. You have to brainstorm ideas. You have to think it through have to try different things. If something doesn't work, you don't just give up on the problem. You try something else until you get the right answer. And so finally, number 17 here. We got two more, 17 and 18. So number 17, I was thinking that was the last one for some reason. Buying plants. David Mackin wants to purchase 9 herb plants. Countryside Nursery has herbs that are on sale at 3 for $3.99. David has a coupon for 25% off and an unlimited number of herb plants at the original price of $1.75 per plant. So part A, we're going to determine the cost of purchasing 9 plants at the sale price. Okay, so the sale price, the sale is 3 for $3.99. Purchase of costs, or purchasing 9 plants. So you'd have 3 times the 3 at $3.99, so we'd just be multiplying 3 times $3.99. 3 times $4 would be $12, so we would subtract 3 cents from that, and we would have $11.97 at the sale price. Remember, these come in $3.99. This is for a pack. Let's say a pack of 3. 3. It doesn't say for a pack of 3, but I'll say that. So it's a pack of 3. So 3 times 3 gives me the 9 plants I need for that. For part B, price of $1.75 per plant, and a coupon for 25% off those. So you want to take $1.75, multiply it by 9, and see what that gives me. So $1.75 times 9 is $15.75. And then we want to take 25% off of that. And so we could take this times 0.25. This would equal, why don't I, so you don't think that 15.75 equals that times that. I'm going to say this, and then 15.75 times 0.25. There we go. Just so you don't think that this would equal that times 0.25. Let's see what we got here. So this times 0.25, that's going to be the amount off. So $3.94 off. And so we would take, the sale price is going to be $15.75 minus the $3.94, which would equal, let's type that in here, $15.75 minus $3.94 gives me $11.81. $11.81, there we go, with the coupon. Okay, so that's my answer part B. This was my answer part A, which is the least expensive way, and by how much. So if I take this and this is less expensive. So coupon is less expensive. And by how much, you might be able to do that in your head. I hope you can, but if not, you could take a calculator if you really needed to. But this would be 16 cents. It's that much less. Alright. And so I wanted to show you one more quick thing about this. You may have noticed, well, I subtracted 25% and I got this. Could I have just multiplied 15.75 times what it would actually be, times 0.75 then? Could you get the answer from that and get the same thing? Let's try that. And so if you took 15.75, multiplied it by 0.75, there's your answer. So you could get the price that way too. So if you take 25% off of 100%, that's what you're actually paying for. You're paying the 75% of the original price. So that's the same thing there, $11.81. So you could think of it like that as well. But this is the same thing as that, just taking away a step basically. You don't have to subtract the amount off. Alright, and now we're at the last one, 18. Setting the switches. And how many different ways can a panel of 4 on-off switches be set if no 2 adjacent switches may be off. So no 2 adjacent just means, this part just means right next to. So they can't be right next to each other. So let's brainstorm some ideas with this. Okay, so I'm going to split up this into some different parts. I'm going to draw pictures. So this is going to be kind of like situation number 1. This could be on. And so I'll say, I guess I'll just write the word on. So this could be on, and then these ones, what could you have? So this is on. This could be off or on. It wouldn't make a difference. So you'd have one possibility here times, let's just write down all our possibilities. So this could be off or on. And so I'm going to say that's another possibility. These can be like that. And then this one, no 2 adjacent switches could be on. So this would have to be on. And then you'd have 2 more possibilities branching off of that. So this, you'd have this, and you'd have this right here. So you could have that same thing, and this could be either off or it could be on. With this situation, if they're both on to start, so let's say this was the one where it was on to start. These are your possibilities when just number 1 is on. When both the first 2 are on, these are your possibilities. Now for this, you could have on, and I'm trying to make it so that this is, my first one is where it is off, just thinking of all the different combinations I could have. So this would be on, and what if this was on? This one could be off. Could they all be on? Sure, they could all be on as well. Okay. Now what's another possibility? You could start with this being off. If that's off, this has got to be on. But then you've got choices here. So if this one's off, then that would be on, and then this one could be off or on. So that's one possibility there. If this was off, this would have to be on. This could also be on, this could be off. And if this was off, I see another possibility here. You could have this being on. You could have all 3 of them being on if that first one was off. And as I continue to think through that, you couldn't have another possibility here. This could not work. If you did off and off, that doesn't work, because then you have 2 adjacent switches being off. So a combination like this, I would say no, sorry. And so I feel like we've done well. We've got on, off, on, off. If you start off with on and off, then you've got either this can be on and off, or this can be on and on. If you start off with the first 2 being on, that one could either be off, and then that would be on, or it could be on and off, or it could both be on. And if you start off with this combination, off and on, and off and on, if you start off with off and on, I'm saying off and on so much here. It's starting to just sound weird. But anyways, off, on. This is a possibility, off and on, or you could switch that on and off. 2 adjacent ones that are that way, and off and on. So this is the combinations that I see. You had these 2 combinations with the off on, or on off possibility. With the first 2 on, you've got these 3 possibilities. With the first off and the second on, you've got these 3 possibilities. And this isn't a possibility to have anything else like that. And so these are all the possibilities I see. And if I look in the book, that's what they got. So 8 possibilities. How many different ways? There are 8 different ways. There may be an easier way to do that problem, but that's the way I saw it first, and so that's the way I did it. If you can think of an easier way to do this one, maybe I'll give you some bonus points if you can show me an easier way to do that one. but that way works. It just kind of went through all the possibilities. So go back, review any of these problems that you feel like you're still not feeling too confident with, and hopefully you found that helpful. Hopefully you appreciate a masterpiece when you see one right there, and another sort of masterpiece. Right there, Van Gogh, whatever. Yeah, right there. That's where it's at. Go Carla, cutting that board into 4 equal pieces. Good work right there. All right, so hopefully you found that helpful. Let me know in class before it comes to test time, not right before you're going to take the test. Let me know during tutoring, something like that, if you have any questions. Thanks, guys.